Hello, I am Rahul Gopinath, a postdoctoral researcher at CISPA Helmholtz Center for Information Security. My talk today is about mining input grammars. So why do we need input grammars? As you all know, there is a huge growth in bugs and vulnerabilities year after year. And it is important to make our systems robust so that we can prevent them from being exploited by malicious actors. The best way to make our systems robust is extensive testing. And automatic testing, especially fuzzing, can help here. Fuzzing is fairly simple. The idea is that no system should crash when given any input. So fuzzers try to generate random inputs that can induce crashes in the system under test. So here is how we fuzz. We generate random input which is then fed into the program. If the program crashes, we have found a likely vulnerability because the input was unexpected by the program. That is, there was a logical flaw in the program that could be subverted by the attackers. Fuzzing is effective if the fuzzer can generate sufficient inputs that can exercise all parts of the program. Unfortunately, traditional fuzzing is really bad against any kind of structured data. The problem is that it is difficult to generate inputs that conform to complex input specifications. The traditional answer to guiding a fuzzer through complex program paths is to use a coverage-guided fuzzer. Unfortunately, such coverage-guided fuzzers perform very poorly when dealing with programs with complex input specifications such as parsers. Another technique to generate high coverage inputs is by use of symbolic execution or to use a systematic constraint solver to direct the fuzzer. Unfortunately, such solvers have a problem with the extremely large number of paths that are present in the program with complex input specifications such as parsers, the so-called path explosion problem. So effectively, traditional answers do not help. So what we need is a grammar for the input parser so that we can get past the parser. Now, grammar-based fuzzing is not a new idea. A number of fuzzers use grammars to generate inputs. The bigger question is, where can we get these grammars from? The actual formal specification of a program is notoriously hard to obtain. Let us take the ideal case, when there is a well-known standard for the format. Unfortunately, even in the ideal case, we have to contend with buggy implementations or extra features that the developer decided to include. For example, there are a number of GCC extensions to the C language which are not specified as a formal grammar. Then there is also the built-in error tolerance for inputs in a number of programs such as browsers and parsers that make it accept invalid inputs in the name of convenience. So here is an example. We all know about JSON, which is quite a simple language that can be specified in the back of a business card. Unfortunately, even such simple specification is notoriously difficult to get right. This is the evaluation of whether JSON parsers conform to the JSON specification by SIRIT. The y-axis lists various parsers and x-axis are the various common misimplementations, and these are the results of evaluation. The green color represents places where the test passed, variations of yellow and red represents where the test failed, and the blue represents where it was unspecified. Ideally, it should all have been completely green. But you can see that almost no parser actually implements the specification correctly. Unfortunately, even in most cases, there is not even a specification, and even if programmers started with a formal specification, it can get out of date really fast. Essentially, for handwritten parsers, documented grammars are untrustworthy. The problem is that effectiveness of our fuzzing is directly dependent on the input features that were present in the grammar. Any missing input feature is a blind spot. So where do we get the grammar from? Our key idea is that handwritten parsers written in a recursive decision fashion already encodes the grammar. Our technique first extracts the dynamic control dependence trees from given sample inputs that cover all features of the program. Then it combines these trees into a general grammar. So what is a control dependence graph? A control dependence graph is a graphical representation for the program where each statement gets a node and there is a directed arrow between control dependent nodes. A statement B is control dependent on statement A if A determines if B executes. A dynamic control dependence tree is similar to a control dependence graph, except that we use statement executions. So to this tree, we attach input characters. Each input character is attached to a leaf node that accessed it last. This makes the dynamic control dependence tree a parse tree. And here is an example parse tree for the arithmetic expression 9 plus 3 by 4. Now there is a bit more to be done to make these parse trees accurate. In particular, you may notice that not all nodes that are named while are compatible with each other. That is, you cannot replace a number with an arithmetic operator and expect a valid input value. So we will see how to deal with them next. For example, here we may not be sure if the two while nodes are compatible. So what we do is to swap them and check if the resulting input is valid. If they are, then they are compatible. That is, they represent the same non-terminal. And we represent compatible nodes with the same color. Here is another example. We check if the two parse expression nodes are compatible. Here, instead of swapping, we simply replace the larger one by the smaller one. If the nodes are compatible, simple replacement should also work. Since it produces valid input, both nodes are compatible. So they represent the same non-terminal. Here is an example when two while nodes are not compatible. That is, the two iterations do not represent the same non-terminal symbol. So we can now combine the parse trees into a general grammar. The idea is that children of a node from the expansion rule of the corresponding non-terminal. So the parse expression node has two possible expansions from this tree. Similarly, we can collapse the rest of the tree for a preliminary grammar. From this, we can abstract the final grammar. So here is the final recovered grammar from the arithmetic expression parser that we saw earlier. And of course, the grammar generates the expected input stream. Another example is the JSON grammar recovered from MicroJSON. Our technique, which we call Mimit, is lightweight and can be applied for a variety of parsers. The grammars produced by Mimit are well readable and can be used for a large number of other purposes in software engineering other than fuzzing, like program comprehension, program documentation, clone detection, etc. Now we come to the next issue. That is, for us to produce such grammars, the inputs that we start with should cover all features. However, producing such inputs is difficult. Why not use the seed corpus as instrumentation-based fuzzers such as AFL does? The issue is that when we exclusively rely on seed corpus, the variety of inputs we can produce is determined by the variety of seed corpus. This can lead to blind spots. So we really cannot exclusively rely on seed corpus. So what should we do? To understand how to solve this issue, we looked at several parsers. Here is an example URL parser from the Python source code. What the parser does is to examine input characters, typically 1 byte at a time. This is a JSON parser. Again, what it does is to examine characters one at a time and make decisions based on character whether to continue or discard the input as invalid. That is, these parsers typically proceed one element at a time, deciding at each point whether to discard or continue processing. So if we can somehow provide the correct characters to continue processing, we can eventually produce valid inputs. So this was our key idea. Since a parser typically processes inputs 1 byte or 1 character at a time, we try to construct valid prefixes that are accepted by the parser as incomplete. In essence, we try to get the parser to tell us whether the given input was merely incomplete. That is, whether the prefix could lead to a valid input with some suffix, or whether the input was incorrect in the sense that no suffix exists to make that input valid. So let us say we had a program without specification that we want to generate inputs for. We start with an empty string that is fed directly into the program. This is quickly rejected as incomplete, but our instrumentation tells us that it encountered an EO error while processing. So we add an arbitrary letter A to the input, which is again fed into the program. This is rejected as incorrect, but before rejecting, the last character was compared with different values. So what we do is to choose one of the compared values randomly. Here, an open parenthesis, and we replace the last character in the input string with that value. Then we add one more character randomly here too. The system continues this process until we reach the close parenthesis, and now the system responds that the input is valid. The complete string is parenthesis 2 minus 9 4. This technique effectively turns any parser into a generator, producing high quality inputs without any bias. And our results on parser directed fuzzing was published at TLDA 2019. While simple parser directed fuzzing works for many parsers, one place where it does not work is when the input goes through a tokenization phase. That is, before parsing, the input is split into tokens and assigned specific categories such as letters, digits, arithmetic operators, etc. The stream of such tokens are then parsed. The problem with tokenization is that simple chain tracking of strings no longer works. This also has an impact in grammar mining because we rely on being able to recover where an input index was accessed last by the parser. Another major problem with tokenization is also that there are a wide variety of patterns for tokenizations, any combination of which can appear in a program. So handling tokenization is not simple. We also needed to stop as soon as parsing phase was over. However, we succeeded in transferring the input chains across the tokenization phase without imposing significant penalties on program execution speed. And our work was published at ISTA 2020, and this work also served to improve our grammar mining techniques. Now, together, both techniques effectively allow us to turn any parser into a generator, producing high quality inputs without any bias. Unfortunately, this technique is rather slow. The problem is that each character advancement in a single input costs at least one execution. That is, if we have to construct an input with 10 characters, we need to expend at least 10 executions to get there. And not all inputs can actually be used. Some of the input prefixes may not actually result in a valid input. So this can cause a significant reduction in the speed of fuzzing. So instead of using them directly, we use it in combination with the grammar miner. We use directed fuzzers to explore, then we use grammar mining to generalize, and again use the directed fuzzer to refine. The grammars that we mine in this fashion are sound and complete up to context free, are well structured, well readable, and well maintainable. And such grammars can be used not only for fuzzing, but also for other software engineering tasks such as program comprehension, refactoring, clone detection, debugging, program repair, validation, and documentation. So in summary, I have shown you why grammars are important for fuzzing, how to recover such grammars from given program and sample inputs, and how to generate unbiased sample inputs for grammar recovery. Thank you for listening to my talk, and I am open to questions.